Hello class, in this video we're going to be looking at Hamiltonian paths and Hamiltonian cycles from exercise 14c. The learning intention of this video is for us to understand and recognize what a Hamiltonian path and Hamiltonian cycle looks like, and for us to understand how Hamiltonian paths and cycles differ from Eulerian trails and circuits. Let's look at what Hamiltonian paths are. Now, if you recall what a path was, in our previous lesson, we said a path was where you've got a route with no repeated edges and you've got no repeated vertices at all. A Hamiltonian path, on the other hand, is a very specific type of path where you have to visit every single vertex that exists in that particular network. Let me show you an example of this. So if you look at the example on the right hand side over here, notice that in this particular network, I'm going through every single vertex that exists in the diagram. And if you go through every single vertex, it makes it Hamiltonian. I would also like to add a few things. When you're drawing your Hamiltonian path, you can actually have multiple solutions that exist. So in other words, what that means is that you can actually draw a Hamiltonian path that starts at different points. So notice over here, I've started at that particular vertex, but technically I could have started at any other vertex and still draw a Hamiltonian path. So I could have started over here, for instance, as well. Another thing that I want to point out is that when you do have a Hamiltonian path, notice that I'm not actually going through every single edge. So notice that I'm not going through that edge or that edge or that edge at all. And lastly, just recall that for a Hamiltonian path, you cannot have any repeated vertices whatsoever. On this slide, I'm showing you guys another example of what a Hamiltonian path looks like. The reason why this particular graph over here is showing a Hamiltonian path is because A, it's going through every single vertex or every single city that's listed on this particular graph. And B, notice that you're starting and ending at different vertices as well. What I'd like you to do now is I want you to identify whether the following network below contains a Hamiltonian path, and I want you to justify your answer by writing a sequence of vertices. So for this question over here, I'm going to show you two possible answers. As I said, you can actually have multiple solutions that exist, and your answer might be slightly different from my answer. But in my first example, I'm starting at D and I'm ending at G as shown by this illustration here. Alternatively, I could start from C and then end at A as shown over here as well. Have a go for this question. Can you see if this particular network contains a Hamiltonian path? So for this question over here, it's actually not plausible at all for us to draw a Hamiltonian path, because if you've got three odd vertices over here, there's no chance that you could actually start from one and then go through every single vertex without actually repeating an edge. Have a go for this question. So for this particular network over here, it is actually possible for us to draw a Hamiltonian path, and I'm showing you guys this diagrammatically as well as listing down the sequence of vertices. So again, I just want to emphasize that you don't need to go through every single edge for a Hamiltonian path. The next thing I want to be talking about now is Hamiltonian cycles. So if you recall what a cycle was, we said that a cycle was a specific type of route where you've got the exact same starting and ending vertex. And because you've got the word Hamiltonian over here, that just simply means that you need to go through every single vertex, but the starting and ending vertex are the same. Look at the example on the right hand side so you can see what I mean by this. So in this example over here, notice that I'm starting at vertex A. I go through every single vertex, but again, I end up at vertex A as well. Similarly to a Hamiltonian path, you can have multiple solutions that exist. You don't need to go through every single edge, and again, you need to always start and end at the exact same vertex. On this slide over here, this is showing you another example of what a Hamiltonian cycle looks like. So in this example, you started at this vertex, I'm going through every single vertex in the network, and again, I end up at that vertex. I do want to conclude by saying that unlike Eulerian trails and circuits, which we looked at previously, there's going to be no simple trick or rule for us to determine whether a network contains a Hamiltonian path or cycle. So if you can recall back to our previous lessons, we said that Eulerian trails and circuits can be identified by analyzing the degree of all the vertices. We said that when you've got exactly two odd vertices and all the other vertices are even, then you've got a Eulerian trail. In contrast, when you've got all the vertices with an even degree, then you've got a Eulerian circuit. However, if you're trying to find out whether a network contains a Hamiltonian path or cycle, unfortunately there is no nice neat rule for us to use to easily detect it, and so you're going to need to do it through a process of trial and error. Have a go with this question. Can you identify whether this network contains a Hamiltonian cycle? And if so, I want you to list down the sequence of vertices. So for this particular question, A Hamiltonian cycle does exist, and I've got one possible solution listed down below. Have a go with this question and see whether you can identify whether it has a Hamiltonian cycle by listing down its pathway. So for this question over here, I am able to actually find a Hamiltonian cycle where I start at I and I end up at vertex I as well. To get further practice, what I want you to do is I want you to answer all the remaining questions from exercise 14C. So there are 8 questions in total, and you should have answered questions 1 to 3 in our previous lesson. This is the end of the video. Thank you for watching, and I'll see you guys again in the next one. Bye.